good morning, good afternoon, everyone. Today we are so happy to have Professor Jayachandran. He's professor of physics working at Radio and Space Physics Laboratory Physics Department, University of New Brunswick. His research focus is on the solar wind, magnetosphere, ionosphere system. He and other research collaborators measure the ionosphere to understand the relationships between the solar wind, magnetosphere, and the ionosphere using a number of ground-based radio and optical instruments located in Canadian Arctic. His research areas include development of radio and optical techniques, solar wind, magnetosphere, and ionosphere coupling, ionospheric irregularity and structures, and the electrodynamical coupling between different regions of upper atmosphere. He has participated and involved in different projects, for example, the Canadian Geospace Monitoring Program, Canadian High Arctic Ionospheric Network, development of empirical Canadian High Arctic Ionospheric Model, SuperDAM, swarm satellite missions, EPOP satellite missions, Canadian Space Science Data Portable, etc. He has been the chair on the vice chair of different academic organizations. Today, he will give the talk titled Importance, Perils, and Limitations of High Sampling of GNSS Signals for Ionospheric Research. So, Professor Jean, so you have the floors.
Okay, thank you for that introduction, and thank you for inviting me to give the talk. Can everybody hear me clearly? So this talk, I'm going through some of the problems of when we reach certain limit in our technical capability for any measurements. Doesn't matter whether it is ionosphere or in lab measurements of certain physics phenomena. We are playing with the experimental limitations in terms of measurement accuracy or precision, as well as technical capabilities. So I'm going through one particular aspect of this, that is for using high sampling for ionospheric research. So that is my talk outline. I'm going to give you brief introduction and then going through the motivation why we are doing this, and why we need high sampling, and then going through the importance, limitations, and perils associated with high sampling data, and then some concluding remarks. So as you may all know, ionosphere, it's an ionized part of Earth's upper atmosphere. Starting about 60 kilometers, there is no well-defined lower boundary, and all the way up to 2,000 kilometers. Again, not well-defined boundaries. It depends on various conditions. And the primary source of ionization is sun and its solar UV. And in the high latitude, where I am mostly concentrating my work on, we have additional source of ionization in terms of high energy particle precipitation that follows the magnetic field lines. So going back, so the ionosphere, sorry about that, temporal variations from milliseconds to a few thousand kilometers. That depends upon the type of structure that you're looking at. Certain plasma lines in centimeter, millimeter scale, and continental scale tongue of ionization that few thousand kilometers. So we are looking at different scale sizes of ionosphere. And then if you look at the right-hand side of So if you look at the irregularity spectra in terms of the scale size and the wave number, if you want to look at that, you can see that you have large scale features in this region, all the way to lower scale features or small scale features, plasma lines that is in this scale. So that is the synthetic spectra of ionospheric irregularities that we are dealing with. In order to measure the spectra or the whole range of the scales, we need to have different sampling rates. So if we want to measure some of the large small scale structures in terms of temporal variation and spatial scales as well, we need to have high sampling. So that is one of the requirements, one of the need for high sampling. And as I said before, spatial variation extend all the way from few centimeters to thousands kilometers. And other than understanding the physics of various aspects of ionosphere, there are many applications that uses ionosphere. Ionosphere is a medium. It's a plasma. That means it affects anything that, any signal, any radio signal that goes through it. So ionosphere will have significant impact on navigation and communication and timing systems. And one of the things we forget when we study about ionospheric impact on signals and systems is basically the effect or the impact is scale dependent. We use most of the time we do ignore that aspect of our application. And when you look at the GNSS based applications, I'm broadly categorizing this into three groups. One, safety of life, that needs high precision, high integrity, as well as standards and regulations and continuity, availability, and accuracy. So those are the safety of life systems that depends on GNSS-based systems. So if you look at that, transportation, public safety, satellite communication, military, etc., etc. That is one end of the spectrum that needs high precision, availability, regulatory standards. And the other end is the mass market. That means people use GNSS for position and timing application for various recreational purposes, for personal communication and navigation, cell phone, for one example. And then recreation, people do GNSS, use GNSS for hiking and other various aspects of this. And then commercial vehicles, trucks and buses, and recently Internet of Things and location-based services. So they don't care much about the integrity and accuracy. They want to reduce the cost. So low-cost solution, user-friendly, as well as whatever the best performance that is available out in the marketplace. So that is the other end of the spectrum. One end we have safety of life, other end we have mass market, and in between we have professional applications that requires high precision, high accuracy, and high reliability. And those are the various fields that uses that professional services though. And there are commercial services available for these purposes. For fundamental research purpose, we need close to reliability and availability. That means, in my opinion, there should be close to the safety of life aspect of systems. Okay. So those are the applications that uses GNSS systems, but the performance of and the accuracy and precision of GNSS measurements depends on the how we treat the ionosphere. So for most cases, I'm quantifying the impact of ionosphere on the systems as in two categories. One is deterministic. That means if we know about the ionosphere, if we can measure the ionosphere precisely, we can correct for those effects in these systems. For example, total electron content variations. For example, if we use multi-frequency measurements, GNSS measurements, we can account for the total electron content, or we use that measurement to estimate the total electron content. In turn, we can correct the positioning and accuracy, TEC-based performance. So I'm qualifying that as deterministic. If we know TEC, we can correct for it and we can get rid of it completely. And same thing for high frequency propagation. If I know the ionospheric conditions precisely, I can mitigate all those effects. And then second aspect is stochastic. That means even if you measure certain aspects of it, we will not be able to correct those effects from these measurements. Example, I'm giving you some example, diffraction and scattering of the signal. One example is scintillation. That means rapid fluctuations in amplitude and phase of the signal. We cannot mitigate those effects from our measurements. If they are there, we have to live with it, with knowing that whatever the measurement we make under those conditions will not be useful for any applications. So on the right-hand side, I'm going to show you one of the measurements from one of our chain stations. So top panel is the electron density that is based on an ionosonde measurement. So you can see a lot of structures in it. And same time, you can see the fluctuations in total electron content in the middle panel. And bottom, a spectrogram of this, you can see different scale sizes, and some of them will be stochastic, and some of this will be deterministic. So whenever you make ionosphere and there is irregularities present in the ionosphere, we have to deal with these two effects. On the bottom panel, it's an oblique HF sounding or oblique ionogram. Here you have a quiet ionosphere. You can see the propagation character clearly. You can see the O and X. And if you look at the Doppler spread of the signal, it is very, very small. But when irregularities are present in the propagation path, you can see the signal is now Doppler broadened. That means some of the system that cannot handle this broadening or due to bandwidth limitations will not perform. So these are the tests we did in the Arctic under different conditions. So some of them we can deal with, some of them we cannot. And scintillation have a different effect on systems and measurements. So here I'm showing you a case where time is along the x-axis and relative error in the position in meters, horizontal error, and this is vertical error under scintillation conditions. So you can see this is an equatorial region, activity or sunset. When you have pre-reversal enhancement, you have a lot of ionospheric irregularities are present, and you have scintillations, and that produces few 100 meters error in positioning in the horizontal as well as vertical. So these are the things that we have to be careful. And in order to get these, we need to make use of the technology where we can sample at high rate. And some other estimate showing you some other effects of bit decoding error, etc., how they are related to scintillations. We will not worry about that. So these are measurement point of view, but we also have an effect on other, because ionosphere is a medium where signal from all sorts of sources propagate. And for radio telescope, for example, if you are doing radio astronomy, we need to deal with the ionosphere as well. So here I'm showing you the radio telescope imagery. On the left is a quiet ionosphere, This is an animation. I'm hoping you can see that. On the right-hand side, when there are scintillation present, you can see this fluctuation. That's why it's called scintillation. So that means people will not be able to precisely locate the source, and that will have implications in radio astronomy telescope operation. And the other less known or less studied effect is nowadays the synthetic aperture radar imagery is increasing in terms of their coverage and their usefulness. So again, these are space-based radar that uses various frequencies for various purposes. If you want to use for soil moisture and crop situation, we use X and C band high frequency. And if you want to use canopy and tree and forest, we use VHF or L band frequency. So it depends upon what you want to measure, we vary the frequency. And that means they will have a different effects on the imagery that generate using these frequencies. And longer wavelength because of the nature, dispersive nature of the frequency and the frequency dependence of the propagation, longer wavelength are more sensitive to ionosphere. So I'm going to show you a couple of 4 examples. All top bands are synthetic aperture radar images that has some sort of deformation due to ionosphere. So you can see these stripes, those are ionospheric irregularities. You can retrieve those for studying ionospheric purposes, but I'm not going to go there. And on the bottom, you can see clear images under mostly quiet ionospheric conditions. So you can see the drastic difference between images when there are irregularities and when the ionosphere is quiet. So what we study has long range and long applications. So now I'm coming to the motivation, why I'm going through this stuff. And nowadays, if you look at the world map, there are millions of GPS enabled or GNSS enabled devices that make measurements. There's an explosion in the number of receivers and our number capabilities. Okay. And if you look at the data available out there, openly available data, again, few thousands of receivers worldwide available. But the question you should ask yourself, and I ask all the time to myself, is how good is this data? Okay, because various receivers are deployed and they all have different hardware and software or firmware, and they use different tracking or locking algorithms. And so how good are the performance of these various hardware, firmware, or algorithms for the retrieval of the data? And when we do high sampling, so that means we are playing with the inbuilt assumptions in certain measurements. For example, I'm going to give you for total electron content estimation, we use these 2 or multiple frequency and the dispersive nature of the ionosphere to measure the total or to estimate the total electron content. That means if I have 2 frequencies measuring the same region, so because of the nature of the ionosphere, they will have differential delay between the frequency, and we use the differential delay to calculate the total electron content. But in that case, we are making one assumption that medium or the signal is fully refractive. So that means we have that 1 over f square dependence. But how good is that assumptions under certain conditions? Because, for example, scintillation, during scintillation, that assumptions completely break down. That means you cannot use the refractive approach to calculate TEC. So we don't know what we are calculating under scintillations. So that's the That's what I meant by flirting with the assumption in the underlying physics of the measurement. And then last aspect means these measurements are electronic systems most of the time, and they are impacted by the environmental conditions. That means temperature and humidity and all the stuff affects our measurements, because we are talking about nanosecond delays in the system, and the temperature plays a major role in the propagation delay through the system or through the electronics. So those are the stuff we need to worry about. And if you now look at the literature, you will see some of these plots. I'm not going to name where I took this from for various reasons. So whenever you look at these kind of stuff, they are talking about 0.1 tech variation or fluctuations in the signal. Can we actually measure TEC that precisely? Or if I want to put that in question in reverse, what is the precision of our TEC measurements, for example, using GNSS? That's a question I ask by myself. So, and as I said before, we are talking about different scale sizes of irregularities, and there is a need for high sampling. Here, I'm going to show you an example of our recent paper, one of my colleagues. On the left-hand side, you have the auroral electrojet index, a proxy for auroral electrojet index, top panel. But middle, the one panel below, you have the all-sky imager data. So you can see the auroral oval and the boundary, etc. And then here is the superdone HF backscatter. Here are the chain, our networks, change in total electron content. And this is the change or the phase scintillation index, standard one, and amplitude scintillation index. So these are 1 minute indices calculated. That is the standard. And you can see the auroral oval, you can see the backscatter, and you can see the boundary here. And when you look at here, you can see that during the event of brightening of the arc, you have a lot of total electron content variations. And that is showing up in the phase scintillation index. But when you look at the bottom panel, you will see that during that 1 minute, if you calculate scintillation index using that 1 minute interval, there is not much amplitude scintillation. People think that, okay, there is no amplitude scintillation, but we have phase scintillation. But this is TEC, just TEC variation. Ignore that for the time being. But if we have a high sampling, so we can calculate scintillation index. Instead of 1 minute interval, we can calculate scintillation index using 1 second interval. So then the story is slightly different. You can still have the total electron content variation because that is an entirely different aspect. But the phase scintillation, now it's slightly reduced, or you can say that except during this time, everything else is gone. But now we have dominant amplitude scintillation index. So if you use 1 minute, we have no amplitude scintillation. But if you have 1 second, we have amplitude scintillation. So that means most of the amplitude scintillation producing irregularities in the auroral region, it's in terms of temporal scale, they are much smaller. So that is why we need higher sampling, one of the reasons. The other one, we can, I told you that we can sample up the maximum of 100 Hertz. So here I'm showing you a plot from one of our stations. This is the 100 Hertz total electron content. So this is for a 60-second, 1 minute interval, okay? That plot. And that is total electron content TZ units, usual stuff. But if you enhance this portion of that fluctuation, so this is what you get. That is zooming in on certain part of that data, you will see the fluctuation in total electron content. The question is, are they real or are they due to some other measurement effect? On right-hand side, I'm plotting the total electron content standard deviation for instead of 60 seconds, I'm doing it for 2-hour period. And plotting the calculated noise level that include thermal noise and everything else. And then the higher order ionospheric effects, that is the green line. And the blue line is the sum of the higher order ionospheric effects as well as noise. So that means anything below that I consider as either higher order ionospheric effects or noise. And any fluctuations above that I'm going to consider as real. So that is the theoretical estimate of the higher order ionospheric effects as well as noise. So you can see when you do that, there are certain fluctuations higher than this. So that means they have some geophysical meaning. Okay, how can I prove that they are geophysical? I can look at the co-located measurement using magnetometry. So this is the same data I'm showing before. That is the total electron content fluctuation, standard deviation. So these are the fluctuations I'm looking at. And this is the 1 second standard deviation of the magnetic field variation co-located in the same place. So you can see that these fluctuations are closely related to the magnetic fluctuation. So these are real fluctuations in the ionosphere, real total electron content fluctuations, but at sub-second level. So they are real, so they are useful. They reveal real physics when you have high sampling data. So that is one of the need for high sampling data. And there are many other aspects of it, but due to lack of time, I'm not going to go through all the aspects, all the physics that comes out of high sampling data. But when you sample at a high rate, we are going to introduce some artifact. So this is an example of the artifact of high sampling. So here I'm going to show you top panel. A is the signal phase, fluctuations in signal phase, again, 100 Hertz sampling. And then signal amplitude, again, for the same satellite path or PRN, if you want to call that. So you can see the fluctuations in that. And this is the Fourier transform of phase and amplitude. You can see there are fluctuations has certain frequency. Let's say example, for this case, it's 7 Hertz. So they have a peak in the spectra. Now, if I use that spectral band and do a bandpass filter on the top of the signal, so this is the bandpass filtered signal. So you can see a beat pattern in the signal. So initially, 2 years, we sat on it and we thought that is something real. And this has certain features. So if you look at the spectrogram of this, the frequencies varies with the azimuth, etc. And these are the locations of the satellite. So initially we thought they are real. They have some geophysical significance in it. But then we look deep into it. And this is showing you the yellow or the diamonds, if you want. So that is the peak in the frequency. That is FFT of the signal received, and they show the peak. And the black line is the relative Doppler between two satellites. So those peaks correspond to the relative Doppler between the satellites. It's not geophysical at all. And if you look at the frequency of various satellite combinations, they match exactly to the relative Doppler between these two satellites. So that means the code, which is supposed to be unique for each satellite, is interfering each other, which is not supposed to happen, and they are producing this beat pattern. So it's just code interference. So that was introduced because of the high sampling. If you are looking at 1 second or 30-second data, this will not be a problem at all. But if you sample at high rate, this is the thing that we need to deal with. And if you are just using this without considering the Doppler, we will say, oh, this is scintillation or some ionospheric effect, but which is not. In this case, it is just pure signals interfering, which not supposed to happen, but it happens all the time, or most of the time in the high latitudes. So that is the one of the what do you call peril of using high sample data. It introduce artifact. And the other one is if you calculate scintillation index, classically we average it or standard deviation for 1 minute data for high sampling. But here I'm showing you again a case that is the intensity or the amplitude of the signal in a measure of amplitude. And this is phase. And this is scintillation index calculated using different calculation interval. You can see from 1 second to 5 seconds to 2 minutes. So this is the purple dashed line is the standard data. So you can see the scintillation index you calculate is dependent on the calculation interval. And if you are using scintillation index to quantify the signal fluctuations, you are in trouble because quantification depends upon how you average the signal, which is not physical. And if I were to plot the distribution of phase and amplitude scintillation index calculated using different interval, you can see that distribution significantly varies. So which is, again, a problem, okay? And any quantity that you derive should not depend on the calculation interval if it is physical. Okay, so that is other peril with the high sampling. And then limitations. As I said before, different receivers use different tracking algorithm. Okay, some of them are proprietary, that means patented, and they will not, receiver manufacturer will not reveal it to you. But if you work with them sometime, they will let you into the inner workings of the loop. So I'm going to show you an example. So here I have two carrier phase measurements. So this is using left the time along x-axis and the intensity and phase along difference between phases, L2C. So this is detrended carrier phase using a triple receiver of L2C signal. And this is detrended carrier phase triple using L2P. Okay, so two signals of the same carrier frequency. And bottom panel is the difference of these two. So that means in this triple case, now if I take difference between these two, that is completely gone. That means they are using L2 dependent tracking. So that means they use one frequency to track the other one. Okay, so that's why it's completely removed. And these fluctuations, if I'm using this ionosphere or the signal characteristic is completely lost. On the right-hand side, the same location and a different receiver. So this is septentrion using L2C, septentrion using L2P. And if I take the different, and they use a different tracking algorithm, independent. So they track these two signals independently, whereas Trimble uses one dependent tracking. Now, if I were to take the difference between these two, you have still fluctuations left, and that should be the case because they are not. The fluctuations in L1 and L2 and L5, if you are using, shouldn't be the same. physics-wise. But that is telling you that that is actually the case. If you're using septentrion, these are fluctuations, real fluctuations, ionospheric fluctuations. And if you're using septentrion, you can measure them. But if you're using a triple one, you will not be able to measure them. And this is a problem, right? Because it's due to hardware limitations. And some people are providing septentrion or triple data. They will say, oh, there is nothing during that time. Ionosphere is quiet. But if I'm using septentrion, I'll say, no, it's not quiet. There are fluctuations in the signal. So these are the problems that we need to deal with. And this is, again, because of the tracking algorithm. So this is septentrion when there is a switch in the antenna position. So you can see that currently immediately it adjusts it, whereas there is a significant delay in the other receivers, depends upon when you switch that phase wind effect. So that is what I'm concluding here. Tracking loop performance depends on the algorithm. And for high sampling, you need independent tracking. For example, scintillation purposes or high rate TEZ purposes, you need independent tracking so that we can measure them properly. And any of the parameters that you derive will be useful if you are using independent tracking. So that is the limitations of high frequency sampling. And I haven't considered noise for anything at all. Noise is a problem, and that varies with the different type of receivers. But here are my concluding remarks. High sampling is important in understanding microphysics, but introduces other factors that contaminate the signal. So that is the problem we need to deal with. And also we need to standardize the receiver architecture so that everything provides the same kind of signature because ionosphere, irrespective of the signal or receiver that you're going to use for monitoring, if there are ionospheric signatures, it should show up in the data. It should not be dependent. Ionosphere should not be dependent on and it is not dependent on the monitoring instrument. Okay, and all space weather indices we provide to users using GNSS observable should be thoroughly evaluated and calibrated. We cannot just give them. If I'm giving ROTI for using ROTI as an example, I'm giving you using one receiver means something, using a different receiver means something else. That should not be the case. And also we need to worry about the noise and other environmental factors, which I haven't considered for this talk. We did that, a lot of work on it, but due to lack of time, I haven't considered for this particular talk. And I will stop here and I will try to answer your questions.
Thank Professor Jean. I think this very important questions because always I'm confused about the different this indices for space weather, event or storm this level. So any question or comments from the audience? I think in the chat we have a question.
I will stop sharing and then I will look at the chat.
Yes.
That is yeah, I read that. How do we relate the GNSS data sample interval 1 second, 5 second, 30 second to the ionospheric effects if we are observing short period like 2 hours? That is a good question, but we cannot for a short period of time for a particular, because we need to do a lot of measurements to calibrate the system before we do any provide any services. But you could, for short periods, if you're using, instead of using direct measurements of total electron content or ROTI, or you could deduce the ionospheric free linear combination, which is called IFLC, or using the multi-frequency, you can completely remove the ionosphere. So you could use that and say that if the ionosphere is completely removed from that time series, you can say that all the effects you provide is refractive, and if you have two frequency measurements, you can completely remove them from the data. Again, that depends on 1 second, whether you sample at 1 second or 5 seconds, 30 seconds, doesn't matter. If the ionosphere is gone, it is gone from the data. So that means medium is fully refractive, and you can remove them. But if that is diffractive effects, such as scintillation, that's not quite straightforward. So only thing you can do in that case is to produce a quality fact, that flag that tells it during this time, we have scintillation, and data use at your own peril, because there is no way we can correct or mitigate those effects from the data. So that is a problem. Ionospheric effects depends on the type of variations. Diffraction, you cannot deal with it, you cannot mitigate it. And if people say that you can mitigate it, they are not telling you the truth. Refractive effects, we can mitigate it, or we can remove it completely. So that depends on the effect. So for short duration, it all depends on the effect. Does that answer your question?
I have a question here.
Mm-hmm.
There's the effect, the problem you're talking about. Are they more serious in the auroral region, or how about in the equatorial region?
Yeah, both equatorial and auroral region, it is problem. Mm-hmm. In the mid-latitude, ionosphere is relatively smooth, except certain conditions. And we don't need, I should be careful. We don't need this high of a sampling in order to, because in the equatorial region, we have most of the time scintillation or the fluctuations, ionospheric impact is during after post sunset. That is when you have the pre-reversal enhancement and equatorial spread effect, etc., etc. But that fluctuation is in a completely different regime than the polar or mid-latitude region. So that is basically not weak scattering, it is strong scattering signal conditions. So that means we have amplitude fluctuations all the time when there is spread F. And it doesn't matter whether you sample at 100 hertz or 50 hertz or 20 hertz, we have that effect. But we should remove all the instrumental effect before we provide an answer. So that is in the equatorial region. But in the high latitude region, ionosphere is moving rapidly. So that means these irregularities are moving at few hundred kilometers per second, ionospheric drift speed, if we take an average. So that means we need to have sample at very short interval, these scale sizes. So that has a different effect. But in the mid-latitude region, where the ionospheric is relatively quiet, we don't need to sample at 100 hertz, for example. 20 hertz will do, but most of the time the effects are refractive. That means if you have multi-frequency measurement, you can remove those effects. Does that answer your question?
Yeah, thank you.
But even in the mid-latitude region, we have to be careful about the code interference. They are more frequent than you think, but that only when you are sampling at higher rate. If it is low sampling, the Doppler spreading is not, or code interference is not a major issue.
Yeah, we have comments from the chat. I think, yeah. Yeah, the first comments, you know, the corresponding to the first question, and Bruno says, please comments on the use of different GNSS constellations with different DCB products in TC.
Yeah, I haven't talked about that at all, right? Because that's an entirely different issue. DCB, it's also receiver dependent, tracking algorithm dependent, and all the stuff. So I can't, yeah. So the DCB is a completely different problem, okay? I don't know whether I have that slide. I don't have it here. I have it on a different presentation. So we did study the effect of DCB on different aspects and different types of receivers. It's an entirely different issue. And if you want the problem comes only when you're providing absolute TEC, right? Because if you are not providing absolute TEC, it's not a problem. But if you are providing absolute TEC values for various purposes, it is a problem, and depends upon the type of DCB estimate and service providers. DCBs can vary from 2 TUC unit on average to 8 TUC unit. So for example, if you use JPL ionospheric map or global ionospheric map products, so that has a DCB error of 8 TC units on average. And if you use MIT's matrix database for TEC purposes, that has a DCB error of 2 to 3 TUC units. So it's an entirely different issue. And there is a paper from our group coming up comparing which is the best DCB estimation technique. It's a problem. DCB is another problem. I know that I'm not going to give you, I'm not giving you a full answer, because the nature of DCB is such that I cannot give you a correct answer. Ryan's question, talk about sampling limitation. Do we need different sampling at low and high latitudes to capture different physics? Yes. Short answer is yes. High latitude physics, it's quite dynamic, so you need very high sampling. Whereas in the equatorial and mid latitude, even though equatorial we say it's dynamic, but in terms of the time scale, it is not that dynamic, because they if there is spread of irregularity, they live for at least an hour to 2 hours. They are short-lived, they're long-lived, as well as drift very slowly. Whereas in the polar region, these events are very short-lived and they drift at high speed. So we need high sampling in the polar region and aurora region to capture the physics, whereas in the lower latitude and equatorial, we don't need that high of a sampling. Is that answer your question, Ryan? Okay.
Yes.
I'm still challenged to understand the DCB concepts. I'm coming from surveying geodesy field. So DCB comes in 2 parts if I want to go fundamental level. One is the satellite biases, which are estimated by the providers. For example, code provides you satellite and they correct. So if you look at DCB provided satellite bias provided by them today, and if you look at the same day, so let's say that I'm looking at the DCB for various purposes. Yes, today's DCB, and I can get satellite bias through code. I can get that value, certain value. But if you go back, let's say a week from now, and look at that same value you looked at today, it will be slightly different, because they update, because as they have more and more measurements come in, their clock precision, everything goes up. So there is that aspect of surveying applications. receiver bias are fully a job of the data providers. Let's say that chain, as a chain network, I operate currently around 45 stations in the Arctic. We provide our estimate based on our technique on a real-time basis, okay? So our receiver biases. Similarly, every provider, data provider, if we are using IGS, every single data provider should supposed to provide a DCB estimate, as well as the JPL or Chinese Academy of Sciences or European Space Agency. They calculate DCB based on their own technique, okay? And the JPL bias, if you look at global, using the global ionospheric maps, or European Union DCB estimate, or Chinese Academy of Science DCB estimate, they are drastically, they are different, okay? They are not the same number or value. So, it is a problem, and DCB is also, it's not constant value. It varies, depends upon the environmental conditions. It varies with the temperature. Like say that Arctic, it's cold, antenna temperature is most of the time it's cold, even though the electronics is inside. It varies on various parameters. So to provide an accurate estimate of that, it's problematic. So if depends upon the accuracy needed, if you are looking for millimeter accuracy, I say you go with a different approach to instead of using the BBP or some other stuff, you use some other algorithm for your positioning solution. So that is the best suggestion I can. If you are fully dependent on DCB for your precision, you are not going to get the precision that. Okay, so again, don't use DCB. So DCB to be it's a differential code bias. So that means to put it in a fundamental level. So we calculate TEC or the position using the time, concept of time, right? So we measure the delay, ionospheric delay. That is the one. So if you think about it, nanosecond delay, that is supposed to be, let's say that you're measuring a nanosecond delay. In order for position calculation, you are multiplying that with the speed of light, because we assume that the signal propagates at the speed of light. So multiply a nanosecond delay with the speed of light, you get a significant centimeter in terms of positioning accuracy or precision, centimeter level precision. So that is just pure propagation effect. But then the signal need to propagate through the hardware from the receiver end or the antenna end, through the cable, through the hardware to provide you this. Then there is this propagation delay of this signal within your system. That depends on the electronics, that depends on temperature, that depends on the type of algorithm you're using. So until we have full knowledge of these all delays, we cannot determine DCB precisely. So people use different techniques in terms of estimating this, the average, and I mean, there are minimization of standard deviation, averaging, and assume if the signal, let's say that I have 3 adjacent ray paths, they should have the same delay. And there are a lot of assumptions built in and estimating this DCB. So it is a problem. It is another problem on top of the problem I mentioned. I hope you understood at the basic level and the problem and intricacies of DCBs. It's all clock because it's all time. Signal needs to go from point A to point B through the other electronics and the medium and everything else in between. So that is what we are trying to achieve or trying to measure.
I think they get to know more about DCB, thanks to your explanation. Yeah.
So I'm on time.
Yeah. And again, thanks so much, Professor Jean. Yeah, although we know you are early person, but early morning person, but yeah, still we really appreciate your talk. Yeah.
And thank you for the invitation, and hope you learned something from this.
Yeah, I like your presentation very much, where you look into very detailed this problem or question you address. Yeah. So
yeah, thank you.
Thank you.
Thank you, Professor. Thank you.
Thank you.
Then hope we see each other, maybe, I don't know, online or offline next time.
Okay, I'll be attending AOGS this time. So
Great.
So
yeah, see you
next
there.
time oh, not. Okay.
okay.
Okay. See you.
Bye-bye.
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 Bye.